Recording in progress.
Hi students, in this lecture we are going to learn Gauss law. Let us see what is a Gauss law and its statement. So earlier we have discussed regarding electric flux, right? Now Gauss law is connecting electric flux with the charge. Consider a surface which is closed. It can be any shape. Consider a surface which is closed. Let us take charges Q1, Q2, Q3, Q4, right? Q5. Like this, we can take number of charges. This is a surface which is closed. In earlier lecture, we have learned because of outer charges, there is no net flux through the closed surface, right? That means any field line that is coming from here, it enters and leaves, right? Entering and leaving. So because of outer charges, there is no net flux through a surface which is closed. Okay. But if you take inner charges, because of them, they are only leaving the surface, right? They are only leaving the surface. So now Gauss law states that net flux, net electric flux through a closed surface, it is equal to net charge inside. What is it? Net charge inside by epsilon naught. This is now statement of Gauss. I am repeating. When you are taking a closed surface, the net electric flux through that surface is given by net charge inside by epsilon naught. It is net charge inside upon epsilon naught. Why only net charge inside means? Because we are knowing that due to outer charges, there is no net flux through a surface which is closed. This is what we call Gauss law statement. If you write same thing in terms of integration, it is integral, and we are taking here symbol circle which indicates integration taken over a closed surface. What is it? Integration taken over a closed surface, because we are focusing flux through a surface which is closed. This is indicating closed. And we know how to calculate electric flux. That is integral E bar dot ds bar. So here only changes, we are calculating electric flux through a surface which is closed. Okay. And that is equal to net charge inside upon epsilon naught. This is what we call Gauss law statement. Okay. Right. And here one important point is E bar. E bar is electric field due to all charges like Q1, Q2, Q3, Q4 and Q5. It is because of all charges. But flux is only due to inner charges. The reason is due to outer charges, there is no net flux through a surface which is closed. So in this important one is E bar is due to all charges, but flux is only due to inner charges. Okay. So this is helping us to calculate E bar in more simple way. Whenever distribution of charge is uniform, or you can say symmetric. I can say it is symmetric. Okay. Right. To understand in a more easily, take one simple problem, that is, I am taking a unit positive charge, or you can say plus Q. Charge is now It is a positive point charge. We want to calculate strength of the field because of this charge. What is it? We want to calculate strength of electric field because of this because of this positive point charge. So here first we have to imagine one surface which is closed, because statement is net flux through a surface which is closed. Okay. So first imagine here a surface which is closed, and we want to calculate strength of the field at a distance r from that charge. So here what we are doing is we imagine one sphere by taking the point charge as center and distance as radius. So imagine here one sphere. So imagine one sphere. So I'm taking one sphere here by taking the point charge as a center and distance is r. At that point we want to calculate strength of the field, so taking that distance as radius. So this surface we are calling as Gaussian surface. What is it? Gaussian surface, known as Gaussian surface. Right. See how we are choosing surface. So we have to choose a surface in such a way that this calculation becomes simple. This calculation becomes simple. And see, when this calculation becomes simple, if modulus of E bar same at each and every point on the surface. Next, if between E bar and DS bar angle same at each and every point on the surface, then this calculation becomes more simple. Now see carefully here in this case. Due to positive point charge, field lines radially outwards, right? This is what we have learned in previous lecture. So field lines are radially outwards. Its meaning is, if you consider if you consider a small area on the surface, consider small area on the surface. You can see at each and every point on the surface of the sphere, direction of field is normal. I am repeating, at each and every point on the surface of the sphere, direction of field is normal. It is radially outwards, right? Radially outwards. At the same time, if I'm focusing a small area at a point, its direction, we have learned that area is a vector quantity. It has direction. So here for this small area, so why I'm taking small means, sphere means it is a curved part. When we are taking small area, that becomes a plane. I'm repeating. If we are taking a small area on the sphere, then that becomes a plane and direction will be normal to plane. So one is outwards and one is inwards. Okay. And in our problem, so we are taking outward normal, okay, as direction of the area vector. That means at each and every point on the surface of the sphere, angle between E bar and DS bar is 0. Suppose I'm taking now at this point, E bar radially outwards. Direction of DS bar also radially outwards. Suppose taking here, E bar radially outwards. Direction of DS bar also radially outwards. Right? That means That means at each and every point on the surface of the sphere, between E bar and DS bar. Angle is 0. And we are knowing that since the distance is same from the charge, modulus of E bar will be same. I am repeating, since we are taking same distance from the charge, okay? Therefore, at each and every point, modulus of E bar must be the same. Then see what happens here, calculation part. Closed integral E bar dot ds bar, that is equal to closed integral. I am writing E into ds into cos of the angle between them, that is 0. Since modulus of E constant, I am taking outside. Remaining is now integration of ds. Remember, ds is now modulus of ds bar. Okay, this is a scalar, right? That means now this is equal to, if we consider sum of these small areas, okay, ds, ds, ds like this, that gives us, that gives us the surface area of the sphere, that is a 4 pi r square. Okay, this is now flux, net flux, which is equal to net charge inside, which is equal to Q upon epsilon naught. Okay, from this, see what we get, E equal to 1 by 4 pi epsilon naught into Q by R square, right? That means calculation becoming very simple when you are choosing the surface in such a way that at each and every point between these two vectors, angles same at the same time. If modulus of E bar same, right, the calculation becoming very simple. Okay, like this, we can use a Gauss law to calculate electric field wherever distribution of charge is symmetric. Okay, so statement is net electric flux through a surface which is closed is equal to net charge inside upon epsilon naught. That is a closed integral E bar dot ds bar. So we can write the same thing in terms of differential form. I am writing here differential form. The differential form is del bar dot E bar equal to rho by, where rho is charge per unit volume, rho upon epsilon naught. This is known as a Gauss law in differential form. This upper one is Gauss law in integral form. We are having an integration, right? That's what is known as integral form. And this is known as differential form. Del bar dot E bar equal to rho by epsilon naught. Okay, where rho stands for charge per unit volume. Okay, right. Let us see in notes for this. Yeah, first is statement given here. The net electric flux through a closed surface is equal to 1 by epsilon naught times the net charge enclosed by the closed surface. So closed integral E bar dot ds bar equal to net charge upon epsilon naught. This is net charge inside. That is now statement. Okay. And here important point is E bar is due to all charges, but flux is due to only internal charges. Okay. We are taking only due to internal charges. And whenever charge distribution is symmetric, it helps us to calculate strength of the electric field easily. Okay. And see here one important point. Let us see carefully from the statement. See what we can say from the statement. We have taken one surface which is closed. There are many charges like Q1, Q2, Q3, right? Many charges. Coming to statement, we are giving that net electric flux through the surface which is closed is equal to net charge inside by epsilon naught. Okay, net charge inside. See what happens here. Suppose we are moving Q3 and Q4. We are moving the charges outside, but they are not entering into the surface. Okay, they are not entering into surface, but they are moving outside. So if I'm changing position of Q4 from here to here, okay, I'm changing position of Q3 from here to here. Still, net flux remains the same. But where change comes means intensity of electric field. Okay. Suppose you're focusing electric field at this point. Okay. At this point. When we are changing the positions of charges, E bar may change, but net flux through that surface does not change. Or we can say same thing reverse way. If we are changing positions of Q1, Q2, suppose Q1 change from here to here, okay, this here, from this position to this position. Q2 changed from here to this position. Still, still both are inside the surface. That means net charge inside not changing. Okay, but we have changed the configuration of the charges. Means we have changed their positions. Okay, we have changed their positions, right? But still, net flux is not changing, but electric field strength at each and every point on the surface may change. Is a point clear? As long as net charge inside not changing, but we are changing their positions. Still, net flux not changing, but E bar on the surface at each and every point may change. Okay. So we may expect some simple problems basing on concept like this, right? Okay. So we are saying here E bar is due to all charges, but flux is due to only internal charges, right? So whenever charge distribution is symmetric, it helps us to calculate strength of the field easily, right? Let us solve one more simple question basing on this to get more clarity. Earlier, we have solved due to infinitely thin long wire, due to infinitely thin long wire, suppose charge per unit length lambda. Okay. At some distance r, we want to calculate strength of the field. This is infinitely long wire, thin wire. Okay. So if you remember, we got answer there. E equal to 2k lambda by r, right? So this result we got by taking small elements and then we have taken integration, right? Now we can get same result in more simple way without using integration, just by using GAUSS law. Okay, right. See carefully. So what we are doing here is we want to calculate strength of the field at a distance r due to infinitely long wire which is uniformly charged. Then we are taking here one cylindrical surface. It is cylindrical surface by taking that distance as radius. By taking that distance as radius, So axis of that cylinder is now coincides with that thin wire. Okay, this is R. So we have imagined one cylindrical surface because whenever we want to calculate or whenever we want to use a Gauss law, there must be one surface which is closed. So that is what we call Gaussian surface. So we have taken now cylinder and see why we have taken cylinder. See logically, because of this line chart, field is now it is radially outwards, or you can say normal to wire in all directions, right? In all directions, normal to wire. That means here at each and every point on the surface of the cylinder, at each and every point on the surface of the cylinder, E bar will be normal. Okay. At each and every point on the surface of the cylinder, E bar will be normal. And if you consider small element, why we are taking small element? Because it is a curved part, right? Cylinder is a curved part. So if you take a small area, that becomes a plane. And for that area vector, outward normal is, right? It is along E bar. That means at each and every point on the curved surface, E bar and ds bar, both are in same direction. I am repeating, at each and every point on the curved surface of cylinder, E bar and ds bar are in the same direction. Okay, and we are taking outward normal as positive. That means whenever flux is coming out, that flux is taken as a positive. Okay, right. Now focus top surface and bottom face. Top face and bottom face. So here we are knowing that field lines are normal to wire. That means no field lines are passing through bottom face and top face and bottom face. So flux is only through curved part. Flux is only through curved part. Suppose this length equal to L. Okay. Then this statement is net flux equal to net charge inside. It is lambda into L, right? Charge enclosed by the cylinder is lambda into L upon epsilon naught. This is equal to integral closed integral E bar dot ds bar, right? This is equal to, so what I can write here, integration of E into ds into cos 0, that is equal to lambda L, that is charge inside by epsilon naught. See from this what we can write, take E outside because modulus of E is the same at each and every point on the surface of the cylinder. Remaining is now integration of ds, that is giving us surface area of the curved part, which is equal to 2 pi RL, right? That is equal to lambda L by epsilon naught. So from this, E equal to how much we get? L gets cancelled. It is lambda by 2 pi epsilon naught R, right? So here we got same, right? See carefully here. In the place of K, write 1 by 4 pi epsilon naught. That's what we got here. Lambda by 2 pi epsilon naught R. We got same. And see, we got this one in a more simple way, right? Without taking here integration. So like this, we can solve or we can calculate strength of electric field whenever distribution of charge is a symmetry. That is the advantage of using Gauss law, right?